8.2 Z-scores. Z-scores are a useful method of calculating how likely a data point is among a set of data that is relatively normal. We need the mean, standard deviation, and a Z-score chart to calculate this likelihood. For mean, we use this symbol, the mu, said mu, and the standard deviation is this symbol. Okay? So again, this is only used with graphs that are a normal distribution. So this is not talking about something that is skewed to the right or skewed to the left or something that's bimodal or anything like that. It needs to be a normal distribution. So it's kind of equal on both sides and it's distributed in a certain way. So specific things that we manipulate to be a normal distribution, sometimes grades are done that way. And then there's things that just happen to be that way. So things like height often tend to be shown as a normal distribution. There's kind of the average and then what we expect people to be within and then kind of the unexpected areas on the outside edges. So I'm going to use some basic numbers to represent this. If you have a normal distribution, what happens is that here's your average, and within one standard deviation to the left and to the right, what you'll have is 95% of your data. Again, not 95. It's 68% of your data. Okay? So that means about 2/3 of people would lie in that range if we had something involving people. Within two standard deviations is 95%. Again, rounding numbers slightly. And then within three standard deviations is 99.7%. So we're expecting, again, if this is a poll of most people, that almost everybody would be within that range. If this is 68%, then we know that to the left there is 34% and to the right is 34%. And if this represents 68% and this is 95, the difference between those two is 27%. So that means there's half of it over here, which is 13.5, and half of it over here, which is the other 13.5. And then if this whole range from here to there is 95% of the data, and three standard deviations out, so 3 to the right and 3 to the left, is 99.7. That means that we have 4.7% of the data there. So this is 2.35%. This is 2.35%. Again, I'm using rounded numbers, so you might look online and find slightly different numbers, but they're all relatively close. We're talking within 0.2. On the outside, if you're going to be very accurate, outside would be 0.13% on either side. Okay? So those are very unexpected results. Z-score, the number of standard deviations from the mean, is called the Z-score and can be found by this formula on the right here. So Z is equal to X minus mu over the standard deviation. And X here is the raw data. Mu is the mean, and the bottom symbol there is the standard deviation. Okay, let's try some problems. Example 1. IQ scores have a normal distribution with mean 100 and standard deviation 15. Draw the normal distribution of IQ scores, including the percentages. So if I ask this on a test, simply what I want you to do is draw what looks to be a normal distribution. In the middle here is my average, my mean, which is 100. Within one standard deviation, okay, would be, so 15 below 100 is 85, and 15 above is 115. And so we know that 68% of my data lies there. Next, if we add another standard deviation out, so we add another 15 and we're at 130, or subtract another 15, we're at 70, we would know that from here to here is 95% of my data. It's always 68, 95, and then the last one here is the 99.7. So 3 standard deviations out, so that's 145, and below that is 55, and from here to here is 99.7% of my data. Okay, and that's how an IQ test is actually done. They score it on a normal distribution. So let's apply this to the Z-score. So if you have a Z-score, what is that Z-score to an IQ score of 132? So notice that 132 is up here somewhere. So you are above the average person quite a bit. Actually, you're more than 2 standard deviations above the average person. So your Z-score can be calculated with X minus mu over the standard deviation. So here, this is X. So we have 132 minus the mean, which was 100, and we divide it by the standard deviation, which is 15. And we get a result of 2.13, and the 3 repeats itself. So just like I said, it was a little over 2 standard deviations above. And so a Z-score is just saying how far above or below are you to the mean, and how many standard deviations are you away. Okay, that doesn't have a lot of meaning though, so let's go to example 2 and apply this to some situations here. So the heights of young women are normally distributed. This is key. We have to always know it's normally distributed with a mean of 65.5 inches and a standard deviation of 2.5 inches. What is the probability that a woman chosen at random is below 62 inches? Okay, below 62 inches. So our steps here. Step number 1, we're going to find the Z-score associated with this. So here's our X, our average, the mean, and our standard deviation. Okay, so we do X, 62, minus the average, 65.5, over the standard deviation, which is 2.5. And notice that she is below the average height. And so 62 minus 65.5, and then divide that by 2.5, and you get negative 1.4, and the 4 repeats itself. So she's below average. We saw that already. She was 62 inches and the average is 65. And if we were to look at this chart, if she's negative 1.4, she's somewhere around here, which means, well, at least, I don't know, I'll go up to this chart here. She's, what was the number? Negative 1.4. So she's somewhere over here, which means all of these percentages are above her. So all those people are doing better than her and her height, better, whatever that means. And then these are people that are below her, okay? So it takes calculus to get us some of these answers. And so we're going to steal from calculus here, okay? And this chart here, this is called a Z-score chart. It shows you the percentage of people or of items or whatever it is below. It's always below, okay? So keep that in mind. On this chart, this is always below. So if we go on to here, we see that her Z-score was negative 1.4 repeated. So we go on to this chart and we see here's negative 1.4 on our Z-score. And then here we have rounded to the hundredths, okay? So we get to the second decimal. So negative 1.4 and then 0.04. So it's this one right there. So what that tells you is 0.0749. Let's put this into context. So using the chart, we get 0.0749, which means 7.49% of women are below 62 inches. Okay? So again, what we did was we used our Z-score. We found negative 1.44. We used this number to tell us the number of people below, because this chart always tells you below. B, what is the probability that a woman chosen at random is above 68 inches? So key word in here now is we're looking for above 68 inches. Okay. So here's our x value this time. So z is equal to x, 68, minus mu, which is 65.5, divided by the standard deviation, which is 2.5. And we get 1. So she's exactly 1 standard deviation above the average. So that would be 1 if we want to translate that, 1.00. Again, we go to our chart, and this time we're on positive. So here's our Z score associated with a positive value, so 1.0, and we want that second 0. So it's 0.8413. Okay, so from the chart, we get 0.8413 are below. Remember, the chart always tells you below. So if 84.13 are below, then 1 minus 0.8413 are above. So you do 1 minus 0.8413, and you get 0.1587. So 15.87% are above 68 inches. Okay? So again, what we do is we find out what's below from the chart. Then we can find this. We do 1 minus, and that will get us above. Okay? Let's continue. What is the probability that a woman chosen at random is between 60 and 72 inches? Okay, this is a bit more confusing because we have two values given to us. And what we're given with the chart is we're given something like this. We have some spot we're testing, and then we find out the area below that. But this time we have 60 and 72 inches. So what's tempting to do is just take these two values, subtract them, and then start doing some work with that. But that is not the right process. Let's think about this from a picture perspective in full. So if I know our average is 65.5, right? And we're testing out 72 inches. So let's make this 72. And we want to find out the area below because it's always telling us the area below. And then here, we're testing out 60 inches. Well, 60 inches is over here somewhere below my average of 65.5. And so that's this. And that's what we're trying to get. Our picture is that we are trying to find what percent of people are between 60 and 72. And we're trying to find the area of this in between. So how would we do that? Well, if we take the 72 answer, the percentage, so we want this percentage, and then we subtract this little tail off, what we're left with is what's in between those two values. So this is going to be our approach on this question. Okay, so we're going to take the higher value, figure out the area below, take the lower value, figure out the area below, and then from there we can figure out what is between the two. I'll see if I can work this out in this small area here. So we take our z-score chart, z-score on this first one here. So we have z equals x, which is 72 minus the mean, 65.5, divided by the standard deviation. Punch that into our calculator, and we get 2.6. We go to our z-score chart now, and we figure out the percentage that is associated to that. So a positive 2.6, and 0 is 0.9953. Written as a percent, we have 99.53% of people are below 72 inches. Next, we do this z-score. So we have 60 minus 65.5 over the standard deviation. And we get negative 2.2. We go to our chart. Negative 2.2, we need to look at the negative side here. So negative 2.2 and a 0 is 0.0139. So we got 0.0139 written as a percent. That is 1.39%. Okay. What we said was we would subtract these values. So 99.53 minus 1.39 is equal to 98.14%. So 98.14% of women would be between 60 and 72 inches. All right, so that's how you do between two values. Now let's take one more angle on this. How tall does a woman have to be taller than 90% of women? So some female has a goal of being taller than 90% of women. So here we're given the percent. Okay, so on our Z-score chart, our Z chart, what we're going to do is we're going to find the 90%. So we're going to look in these values in here, see if we can find something really close to 90%. And so if you look right in here, there seems to be a very close value there. So we can do what we want with it. It doesn't have to be perfect here. But I'm going to pick halfway between, so 0.085, just to be a little geeky here. So that gives us 1.285 is the score associated to that. 1.285. Okay, 1.285. So this time, let's work with this formula here. Our goal is to know how tall do you need to be, the x value. So we have z equals 1.285. We don't know x, but we do know the average woman is 65.5 inches tall and the standard deviation is 2.5. So we multiply both sides by 2.5. So by multiplying across, we get 3.2125 is equal to x minus 65.5. Then we can add 65.5 to both sides. So bring the negative 65.5 to the other side, and we get 68.7125. So she should be about 68.7 inches tall. So that puts her at 5'8.7", almost 5'9". Okay, so that's how you work with Z-scores. Sometimes you might need to be creative about how you solve for these areas as we were in C, but it gives us real data in the way that we actually figure out the probabilities that something happens and whether someone like Yao Min is actually this incredibly tall basketball player or if he's just kind of a little taller than average and that's all.